Conservation of mass principle for open system or control volume. The net mass transfer to or from a control volume during a time interval delta t is equal to the net change, whether it is increase or decrease in the total mass within the control volume during delta t. Okay, so conservation of mass for general control volume. Okay, so what is the equation? It is expressed as total mass entering for the CV during delta t control volume minus total mass leaving, mass out, okay, for open mass open volume control volume or open system equals to net change in mass within the control volume during delta t. So we have this equation: mass in minus mass out equals to delta m. Okay, delta of mass net change of mass for open system, or it is if it's a rate over the time, so we'll have the dot at here at the top. Okay. Okay, mass balance for steady flow processes. For steady flow processes, MCV, the mass is constant. So the total amount of mass entering and a control volume equal the total amount of mass leaving it. So mass in equals to mass out, and a rate of mass in equals to rate of mass out. So multiple inlets and exits. We can have a lot of inlets and exits as well. Okay. So mass 1, the rate of mass 1, mass flow rate. Mass flow rate 1 equals to mass flow rate 2. It is also equals to rho VA 1, rho VA 2. Okay, this is from single stream. Okay, single stream. Or we can have two inlets at here. We have mass 1, we have mass 2, and as your input, and we have mass 3 as your output. Okay, so output is the total of mass 1 and mass 2. Okay, so conservation of mass principle for a 2 inlet and 1 outlet steady flow system. This is just an example. Okay, so we the devices that applies these equations are nozzles, diffusers, turbines, compressors, and pumps. Involve a single stream, only 1 inlet and 1 outlet. So we're going to use these equations to solve the problem which involve these devices. Okay, special case for incompressible flow. So the conservation of mass relation can be simplified even further when the fluid is incompressible, which is usually the case for liquids. Okay, so example at here we have mass flow rate for 2 kg per second and volumetric for 1.4 meter cube per second. So this is the outlet. Okay, for incompressible flow we have volumetric flow rate in equals to volumetric flow rate out, because in term of steady and incompressible flow. Okay, so volumetric flow rate 1 equals to volumetric flow rate VA1 equals to VA2. This is velocity, this is cross-sectional area in a steady and incompressible flow for a single stream. 1 input, 1 output. Okay, for steady flow of liquids, the volume flow rate as well as the mass flow rate remain constant, since liquids are essentially incompressible substances. Okay, so during a steady flow process, volume flow rates are not necessarily conserved, although the mass flow rates are. Okay.